So this is our lecture on solutions. This is chapter 12 in the textbook. The chapter starts out talking about water and how water is the universal solvent and can make solutions with a lot of different things. So go ahead and read that section. Solutions are homogeneous mixtures of two or more pure substances. Homo means the same, so a homogeneous solution is when the concentration and the makeup is the same throughout. In a solution, the solute is dispersed uniformly throughout the solvent. Um, you're probably used to remembering that the solute is the solid and the solvent is the liquid. We're going to get into the case here where you see down here where the solute and the solvent can actually be the same phase. So your definition of solute and solvent um, needs to change a little bit. One way you can think of it is solute is usually in the lesser concentration. The solvent is always the dissolver. So go ahead and come up with a definition for yourself that you'll understand. Most solutions are aqueous solutions, meaning they contain water as the solvent and then some kind of solid, liquid, or gas as a solute. And again, you can see examples down here. Solubility is the amount of substance that will dissolve in a given solvent. When something's soluble, generally a lot will dissolve. When it's insoluble, little to none will dissolve. Remember that like dissolves like. Polar molecules and ionic compounds dissolve in polar solvents. Nonpolar can only dissolve in nonpolar. So because water is polar, we call it the universal solvent because polar substances can dissolve both polar and nonpolar. Entropy is a measure of orderliness. In solutions, when you go from a solid to a solution, the order is going to increase. So usually, almost always, the entropy increases with the making of a solution. Intermolecular forces also have a part in this. There are three different things happening when you make a solution. You have forces between the solvent and the solute. You have forces between the solvent and solvent itself, and the solute and solute in itself. And all these forces come together to determine whether or not something will dissolve. So the intermolecular forces between solute and solvent must be strong enough to compete with those between the solute. So how a solution forms. Solvation is basically dissolving. So something solvates, it means it's dissolving. So if we look at these pictures here, this is a solid ionic crystal, and then these are the waters. And what's going to happen is the waters are polar, so they're attracted to the ions, and they pick the anions and the cations off one at a time. So it's just kind of picking each one off. After they pick it off, you see right here, that ion is then surrounded on all sides by water. And the reason for that is so it doesn't go back together. So once all the solid crystal has been dissolved and all the cations and anions are surrounded, that's when you have a solution. So when we talk about solubility and saturated, unsaturated solutions, that definition can be easily understood here. Because if you see, since you need, several water molecules for each single anion and cation, that's why in general you need a whole lot more solvent than you do to solute. So when something is saturated, when you have a saturated solution, that means that every water molecule is occupied holding off an anion or cation. Unsaturated is when there's still water molecules available to pick off more solute. So if an ionic salt is soluble in water, it's because the ion-dipole interactions are strong enough to overcome the lattice energy, and it can break apart the lattice. So see here we have NaCl, and you can see there's a cation, the sodium cation, and the chlorine anion, and it is surrounded on all sides by water. So these two things are dissolved in water right now. This is again just what we just talked about, the solute-solvent interactions. In order for something to dissolve, the solvent-solute strength must be greater than the solvent-solvent and solute-solute strength. If the solute-solute is greater than the solute-solvent, there's not enough energy to pull it apart. When those forces are equal, you get a solution. But when the solute-solute or the solvent-solvent attractions are greater than the solute-solvent, that's when you get nonpolar. That's when the things really aren't going to dissolve. Of course, energy is going to change here. There's three processes that affect the energetics of dissolving. Separating the solute particles. So separating the solid from itself is an endothermic process. And then separating the solvent particles is an endothermic process. The new interaction, so almost like the new forces that form, is exothermic. So this is talking about the enthalpy changes from separating the solute, separating the solvent, and then forming the new solution. And you can see if we have H1, H2, H3, it's kind of like a Hess's law problem. So if you're going to get the total enthalpy change of a solution, it's the addition of all the steps, which is very similar to Hess's law. This may have a positive or negative sign. Again, that'll tell you whether it's endo or exo. And the enthalpy of hydration is very similar. You add up the steps. This is a state function. So again, if you look at these two pictures, this is showing you the energy going up, up, and then it comes down a degree. And here you can see the energy going up, up, and down, but less of a degree. Really, though, the delta H of the solution is only the difference between the start and the end. That is the state function component of this. It doesn't matter how far up or down it's going. Really, all that matters is where it starts and where it ends. That's the state function idea. This is, again, the thing we talked about, whether it's endothermic, endothermic. You can go ahead and look at that. The factors that affect the solution process, if you have a negative delta H solution, if you increase the entropy, and for positive values, the enthalpy of solution is the increase in entropy that outweighs the increase in energy that it causes the process to occur. We talked about dynamic equilibrium before. Dynamic means moving. So when we get this solution process happening, things are still moving in each direction. It's just the net change is zero. Again, a saturated solution is when you have the maximum amount of dissolved solute. Unsaturated is when there's less than that. And a supersaturated solution is a very particular type of solution. What happens is you heat up the solvent. And when you increase the heat, you increase the solubility, so you're able to dissolve more. And then what happens is you slowly cool the substance and the particles actually get suspended. And when they're agitated, they will fall out. So things that affect solubility, temperature. So for solids, when the temperature goes up, the solubility goes up. But for gases, the opposite is true. The solubility goes up when the temperature goes down. Henry's law is the relationship between pressure and solubility. It is a direct relationship, which means as one goes up, the other goes up. You can see the two equations here, the Henry's law constant, how you can calculate that. This is just a picture showing you that idea as well. There's a number of ways to express solution concentration. The qualitative way is simply just using the words dilute and concentrated, just showing you how much solute is dissolved. Numerically, quantitatively, there's several equations. The big one you absolutely have to know is molarity, which is moles of solute over liters of solution. You have to know how to do molarity. Molality has been taken off the AP exam, but it still is not a bad idea to understand it. That is moles of solute over kilograms of solvent. Notice, molarity is the whole solution. Molality is just the kilograms of solvent. Percent by mass is just any percent problem, part over total. In this case, we're talking about solute over the whole solution. Parts per million and parts per billion you're not likely to see. They're actually very big in environmental type things. We're talking about, concentration of things in the atmosphere, et cetera, and so forth. And volume percent is just like we talked about, but in this case, it's just for volume. These three, again, you probably will use. Mole fraction we did before with gases, but this time it's moles of solute over moles of solution. A mole percent comes from that. And normality is a very interesting one. It's equivalence over liters of solution. That's more when you're talking about equilibrium things. Non-volatile electrolytes lower the vapor pressure of a solute. Remember, non-volatile means not easily evaporated. An electrolyte means ions dissolved. So non-volatile molecules do not enter the vapor phase because they're not volatile. That means there's fewer molecules available to affect the vapor pressure. Dissociation of ionic compounds has nearly 2, 3, or more times the vapor pressure lowering. Raoult's law has to do with vapor pressure lowering. Again, not likely to see this, but it's good to know this relationship in the graph. A non-ideal solution is when both compounds are volatile. Basically, both compounds easily evaporate. You can modify Raoult's law. You're very likely not to see this, but that's just a modification of the other equation. Ideal solutions, liquid-liquid solution that obey Raoult's law. Again, just like gas laws, no solution is perfectly ideal. The negative deviations from Raoult's law, lower vapor pressure, are when you have strong intermolecular forces and you have a delta H that is large and exothermic. And positive deviations are when the solute and solvent are dissimilar, weak intermolecular forces, and the particles easily escape. Colligative properties are properties of a solution dependent on the number of solute particles, but not what they are. So it doesn't matter what you have dissolved, it's just every solution is going to have these properties. The three we're going to talk about is boiling point elevation, freezing point depression, and osmotic pressure. Boiling point elevation is exactly what it sounds like. The boiling point increases with a solution. So if you're going to talk about regular water versus a solution of salt water, the salt water is going to have a higher boiling point. The degree to which the boiling point changes can be used with this equation. Kb is a constant, so you would have to be given it. So when you're making pasta, you put salt in pasta water, a common misconception is the salt makes the water boil faster. It does not. The salt is really there to flavor the pasta, but when you're making pasta, you should boil the water first and then add the salt. Freezing point depression, again, is just what it sounds like. The freezing point is lowered when you add something in solution. So again, here's the same equation, essentially change in temperature, Kf is a constant. This is why we salt roads during snowstorms. When you salt the road, you lower the freezing point of water so that the water on the road doesn't freeze as easily. Osmosis is the flow of solvent molecules through a semi-permeable membrane. Solvent, remember, is the dissolver, and usually it's water. So it's the flow of water through a membrane. It has to do with concentration. The water will move until the concentration of solution is equal on both sides. Notice the amount of water will not be equal, just the concentration. And again, this is just showing you when you get equilibrium with osmosis, you're going to have a net change. The water is still moving, just the net change is zero. This creates osmotic pressure, which is very important in living things. Dialysis is the transfer of solvent molecules, which is water, as well as a small amount of solute. This has to do with kidney. If you ever hear when people have kidney disease, they get dialysis because your kidneys are supposed to filter the liquid in your body. An isotonic solution is when the osmotic pressure is exactly equal. Crenation is when cells are placed in hypertonic solution, lose water, and shrink. And hemolysis is when cells placed in hypertonic solution and swell. Those two things, if you remember, we talked about in biology. You can go ahead and look those up. Reverse osmosis is when you have external pressure applied to solution and the water goes the opposite way. So instead of like flowing downriver higher to lower concentration, it flows up. Concentration impurities such as salt remain in the solution. The pure solvent is recovered on the other side. So this is how you get the solvent out. So this is showing you reverse osmosis. You're having pressure go to one side so that the pure water goes through instead of all the solute. The Van Hoff factor I is a colligative property relationship. It gives you a whole number. So if you look to the right here, you can see some I values for NaCl and BaCl2. Values of I are less than expected due to ion pairing. You most likely will not see this, but it is important just to have an idea. Values of I are closer to the expected, the more difficult, more dilute the solution becomes. You can incorporate the Van Hoff factor in the boiling point elevation and freezing point depression equations. Notice you just multiply by I. So if you're given an I value, all you really do is just plug it into the equation. A colloid is a type of homogeneous solution where the particles are very, very large. Milk is a colloid, yogurt, whipped cream, jello. There's particles suspended in a medium, and the particles are actually larger in size. They're not huge, but they're larger than normal. The Tyndall effect is the scattering of light by particles. Light can pass straight through a solution, but will not pass through a colloid. So this is an animation of that. If you have a true solution, particles are dissolved enough you will not get the bouncing of light, but in a colloid, the particles are large enough that you will. This is showing you in real life. So a solution, it will pass right through, you will not see it. In a colloid, you will see the beam. These are just different, again, examples of colloids: fog, smoke, whipped cream, milk, mayonnaise, butter, cheese. Those are all just examples of colloids where they have large solute particles. And that is the end of the Chapter 12 PowerPoint.